Welcome everyone to today's explainer for Chapter 6 of our software engineering course. Okay, let's dive into this. A really common rookie mistake is wanting to just jump straight into writing thousands of lines of code. But today, we're exploring the critical master plan that absolutely must happen first, architectural design. Think of this as the blueprint phase. It's essentially the bridge between requirements engineering, where we figure out what the system actually needs to do, and sitting down to write the code for a program. You simply cannot jump from a list of requirements straight into programming without a master plan, and that plan is your software architecture.
Here's our roadmap for today's explainer. We'll cover 1. An introduction to software architecture. 2. Why architecture matters. 3. Communicating with block diagrams. 4. Architectural design decisions. 5. Non-functional trade-offs. And finally, 6. A lecture summary and exam focus.
Right, let's kick things off with Section 1. Introduction to software architecture and our levels of abstraction.
When we design architectures, we actually do so at two distinct foundational levels of abstraction. The first level is what we call architecture in the small. If you're taking notes, definitely jot this down. Architecture in the small is entirely concerned with the internal structure of a single, standalone program. So at this level, the architect is focused on how that one individual program is decomposed into smaller, much more manageable components or modules. And just so you know, our focus for today's explainer is predominantly going to be on this specific level of design.
Now, contrast that with the second level, architecture in the large. This is concerned with massive, highly complex enterprise systems. We're talking about systems of systems that are distributed over different computers. These might even be owned and managed by completely different companies, scattered all across the globe. So just to recap our first major topic, in the small is all about a single program's internal structure, while in the large is about vast distributed enterprise systems.
Moving on to Section 2, why architecture matters and the three main advantages of doing it right.
So you might be wondering, why do we actually need to do this? Why not just start coding? Well, researchers Bass, Clements, and Kasman identified three main advantages to explicitly designing and documenting your software architecture. I really want you to pay close attention here because this is explicit exam-focused material. You need to be able to list and explain these three advantages: stakeholder communication, system analysis, and large-scale reuse. Let's break these down step by step.
The very first advantage is stakeholder communication. An architectural model provides a high-level view of the entire system. And this is absolutely crucial because a system has a lot of different stakeholders, everyone from non-technical business managers to domain experts, right down to the developers themselves. Code is just far too detailed for a manager to review, but a high-level architectural diagram, that's something everyone can look at, understand, and use to negotiate requirements and project planning.
The second big advantage is system analysis. Making the architecture explicit at an early stage allows us to actually analyze it thoroughly. We can evaluate whether the system will genuinely meet its critical non-functional requirements, things like performance or reliability, long before we spend millions of dollars writing the actual code. If the architecture is fundamentally flawed from day one, the system is going to fail to meet those goals regardless of how beautifully the programmers write the code later.
And the third advantage is large-scale reuse. Similar systems very often use similar architectures. If you're building a range of related systems, what we call a product line, you can literally reuse the entire architectural blueprint. As you can imagine, this saves massive amounts of time and money. So, to quickly recap, remember these three advantages: communication across diverse teams, early analysis of system goals, and large-scale reuse of your blueprints.
All right, Section 3, communicating with block diagrams. Now that we know why we need an architecture, how do we actually go about documenting it? There's a pretty interesting debate in software engineering about this. On one side, we have formal architectural description languages, or ADLs for short. These are highly rigorous and precise, but they are very expensive, incredibly time-consuming, and notoriously difficult for non-technical people to read. On the other side, we have informal block diagrams, basically just simple boxes and arrows. Now, while some academics criticize block diagrams for lacking deep technical depth, they remain the undisputed industry standard. Why? Because they are fantastic for sparking discussion across diverse teams. Sometimes, a simple box and arrow is worth 1,000 lines of formal code.
That brings us to Section 4, architectural design decisions.
Let's turn our attention to Section 6.1 in your textbook. So the crucial point here is that designing architecture isn't some rigid mathematical formula. It's a highly creative process that relies heavily on the background and experience of the system architect.
And this brilliantly illustrates that point. Notice how the core decision sits right at the center, branching out into a whole series of fundamental questions the architect has to ask. For instance, they have to decide how will the system be distributed across hardware cores? What fundamental approach will be used to structure the system? What architectural patterns or styles might be used? The answers to these questions effectively become the architectural design.
But I want to draw your attention to one specific question from that wheel, which is arguably the most important one. What architectural organization is best for delivering the non-functional requirements of the system? Posing this specific question bridges us directly into the most crucial part of today's lecture,
Which leads us perfectly into Section 5, Non-Functional Trade-offs. Please make sure to highlight this section in your notes because it is highly testable. We're going to examine how the specific architectural choices you make directly dictate the non-functional characteristics of your program, things like speed, safety, and security. Let's start with performance. If speed is your absolute most critical requirement, your architecture should localize operations into a small number of large components. Why? Because if you have hundreds of tiny components, they constantly have to talk to each other over the network, and that chatty network slows everything down. By using a few large components, you minimize communication delays and really boost performance.
Next up is maintainability, which is essentially how easily a system can be updated or changed later on. If maintainability is your top priority, your architecture is best achieved by using many small, fine-grained, self-contained components. These small components are much easier to understand, they're easier to test, and if one needs to be changed, you can simply update it without breaking the rest of the system. Now, notice the inherent conflict here. I want to explicitly call this out as an exam focus area. To get the best performance, you need a few large components. But to get the best maintainability, you need many small components. You simply cannot have both perfectly. There is a massive tension here, and the architect literally has to compromise and find a balance between speed and the ease of future updates, perhaps by using different structural styles for different parts of the system.
Moving on to security, which, let's face it, is almost always a critical requirement in modern systems. If security is paramount, you achieve this best by using a layered architecture. You place your most critical assets protected deep in the innermost layers, requiring high-level validation to pass through each outer layer before anyone can reach the core data.
Then we have safety, which is absolutely crucial for things like medical devices or aircraft systems. Safety is best achieved by isolating your safety-critical operations into a single component, or very few components. This strict isolation severely reduces the cost and complexity of safety validation, and it ensures that if a catastrophic failure occurs somewhere else, that isolated safety component can still trigger a safe shutdown.
Finally, availability, making sure the system doesn't just go down. This is best achieved by including redundant components. Basically, if one component fails, the redundant backup immediately takes over, keeping the whole system online. This also allows you to run updates on components without having to stop the entire program. So, just to quickly recap all 5 of our non-functional traits, we have performance, maintainability, security, safety, and availability.
And finally, Section 6, our lecture summary and exam focus.
We've covered a really good amount of ground today. Let's methodically review the most important facts that are highly likely to appear on your exam. First, ensure you can define and contrast architecture in the small versus architecture in the large. Second, memorize those 3 core advantages of explicit architectural design: stakeholder communication, system analysis, and large-scale reuse. And third, be prepared to explain the inherent conflict and the necessary compromise between performance and maintainability. I'll leave you with this final, provocative thought. The architecture is the blueprint that dictates the system's speed, security, and lifespan. An architect wields immense power over how successful a software project will ultimately be. So I leave you with this question to ponder. If the architecture dictates a system's very lifespan, is a poorly architected system doomed to fail no matter how brilliant the actual code is? Next time, in our upcoming explainer, we'll explore specific architectural patterns designed to prevent exactly that from happening. Keep reviewing your notes, and thank you so much for joining me today.